Today we start with random variables, and when we talk about random variables, we are actually talking about a function of the outcome. So we make experiments, they are stochastic experiments, they have uncertain results, and when we are talking about those results, we are talking about the outcomes, and when we are talking about a function of the outcome, we're actually talking about a random variable. Now, when we talk about random variables, we are talking about outcomes, but we can think of something like this. We have to talk about a function, a mathematical function in there. So the result should be something that can be mathematically defined. So for example, you can just say that, okay, you roll a dice, you get results, outcomes from 1 to 6. So you have to define your random variable from those outcomes. You can just say that, okay, my random variable x is gonna be, getting a roll of 6 or higher. How many times I have gotten a roll of 6 or higher, okay? Or you can say that how many times I got an even roll or an odd roll, etc. So we will be talking about these kind of functions, and they will have values, real valued functions. They will be real valued functions. So, for example, 3 balls are randomly selected without replacement from an urn containing 20 balls, numbered 1 to 20. What's the probability that at least one of the drawn balls has a number as large as or larger than 17? Now, in here, we're going to define a random variable x, and we're going to say that this x is the largest number drawn, because in the question, we are talking about drawing numbers from 1 to 20, and it's talking about the largest number anyway. So we are talking about a number that is larger than 17, at least equal to, but larger, maybe larger than 17. So we will draw 3 balls and without replacement. So we are picking one, putting it aside, picking another one, putting it aside. We're not putting it back in there. So we can just pick all those 3 balls at the same time as well for this experiment, but still, we are talking about 3 different numbers. So at least one of them should be 17 or greater. We are looking for the probability of this one. So we are just looking for the greatest, the largest number between these 3 should be greater than 17, equal to or greater than 17. This is the probability we are looking for. So I can just say that my random variable is x is the largest number drawn. So from there, we are going to think about how to get this probability calculated. For example, if I say x is 20, then I'm talking about picking 20. Okay, I have picked 20, so which is larger than 17 anyway. And any other number can come with 20. It might be 18 and 19. It might be 2 and 5. It might be 17 and 18, something like that. Doesn't really matter. But the largest number is 20. I have picked 20 already. So from this one, I will just say that, okay, I had 20, so I have 19 more numbers to pick from. Those 2 things, those 2 numbers. So I will just say, okay, choose 19 choose 2 over 20 choose 3. Why? Because 20 choose 3 is the sample space. And for, after I have picked 20, I have 19 numbers left, and I'm going to pick 2 of them, which is going to give me the probability of 0.15. If x was 19, if my greatest number was 19, then 20 is removed from the sample space as well, because my greatest number is 19, so I cannot pick 20 anyway. So I'm removing 19 and 20 together. So I have 18 choose 2. From 18 numbers, I'm going to choose 2 numbers. And I have 20 choose 3 as a sample space, which is going to give me a probability of 0.13. Then again, I have 18 as the largest number. So I'm going to remove 18, 19, and 20, 3 numbers from the pool. So I have 17 choose 2 over 20 choose 3. Now, this is going to give 11.9%. And then I have to pick 17 as well, because it says as large as or larger than 17. So 17 is accepted as a large number as well. So if I pick 17 as my largest number, then I have 16 more numbers left. So 16 choose 2 over 20 choose 3, which is going to give me a probability of 0.10. Now, from these 3 probabilities, I will just add them together, and I will get a probability of 0.15. Now, this is what we were looking for. The probability of x, which is the greatest number, the largest number I have picked, being equal to at least equal to 17 or maybe higher. Another example, now this one is a bit more calculation related, needs more calculation, I guess, we'll see. 3 balls are randomly chosen from an urn containing 3 white, 3 red, and 5 black balls. Suppose that we win $1 for each white ball selected and lose $1 for each red selected. If we let X denote our total winnings from the experiment, then X is a random variable taking on the possible values 0, plus minus 1, plus minus 2, plus minus 3. Now, this X is our total winnings. So I can win $3, I can lose $3, or I can win anything in between. It might be 0, 1, 2, minus 1, minus 2, anything else. So I have a total of 7 different outcomes. Okay, then I have to find the probabilities. Let's start with 0. If I want to have 0 income, 0, winning, then either I will pick 3 red, 3 black balls, which is going to give me 0, 0, 0 anyway, or I can pick one of each, 1 white, 1 red, and 1 black ball. Now, white and red will cancel each other, plus 1, minus 1, and black is 0 anyway, so I will get a total of 0, which means that I can either pick 5, choose 3, picking 3 balls out of 5 black balls, or I can pick 3, choose 1, 3, choose 1, and 5, choose 1, which is, picking 1 white, 1 red, and 1 black ball. Out of 11, choose 3, which is all the sample space. Now, this is going to give me 0.3, probability of 0.3. Now, for 1, for getting a, income of 1, for getting a winning of 1, I have 2 options once again. I can either pick 1 white ball and 2 black balls, which is 1, 0, 0, total of 1. Or I can pick 2 white balls and 1 red ball, which is 2 minus 1, again, a total of 1. And if I pick 2, black balls and 1 red ball, I got 3, choose 1, and 5, choose 2. Or I could pick 2 white balls out of 3 and 1 red ball out of 3, 2 choose 2, and 3 choose 1. Again, I have a sample space of 11, choose 3. From here, I get 0.24. Then again, for getting a winning of 2 and 3, I can just calculate these values as well. Now, here, the important part is the total of all these values, all these probabilities should be 1. But in here, it isn't. Now, if you can, calculate all, sum of all these 4 values, 0.3, 0.24, 0.05, and 0.09, 0.005, and 0.09, you get something along, 0.30, 62 or something like that, I guess. I don't know. But still, it has to be 1, but it isn't. The reason that it isn't 1 is we are missing something. We have calculated all of this for plus 1s, but actually minus 1 is equal to plus 1 as well. And minus 2 is equal to plus 2, and minus 2 is equal to plus 2, because this is symmetric. 3 white and 3 red balls, they are symmetric. So all those values, all these 3 values, should be multiplied by 2 when you're adding them together. Okay, so you actually have 7 values here. 0.3, 0.24 twice, 0.05 twice, 0.09, 0.005 twice, and 0.09 twice as well. Because they are all, those 3 values all belong to minus and plus values together. So their total would be 1. Now, we have cumulative distribution function. Now, the cumulative distribution function is a probability function, actually, and it gives us a probability of a limit. Okay. Now, if you take a look at this version, this, equation, you see that fx, which is the cumulative distribution function, the x value of f, is equal to the probability of x being less than or equal to another x. Now, there will be lots of x's here, so it's going to be, a bit jumbled up maybe. There's a very, easy way of remembering which is which. The capital X, any capital, letter used in here is a random variable. Any small number used here is a scalar, a limit value. Okay, they are limit values. They are scalar values. They are just normal numbers. But these are random variables. The capital ones are random variables. Now, when you take a look at this equation, you see that okay, there is a random variable here. It's being limited from above. It has an upper limit of x, and this version, and in this version, the probability of x being less than or equal to x can also be written as fx. This f is the cumulative distribution function of the random variable x. So we can just say distribution function as well. It's the same thing, cumulative distribution or distribution function. But we usually write it CDF in abbreviation, or we write distribution function. We don't write cumulative distribution function that much, but they are both the same thing, so it's okay. How we write it isn't really that much important. So this distribution function is the sum of all the probabilities up to a point, up to a limit point, which is x in here. So from here we have some small, propositions or correlations or stuff like that to take out from. The first thing is, if a is less than b, suppose that a is less than b, the event x is less than a is contained in the event x is less than b, because a is less than b. So the first one is contained is a subset of the second one, let's say. So fa, the distribution function, the cumulative distribution function of a, the value of a, is less than fb. Now, this is expected because a is less than b, and f is looking for the upper limit. So looking through all the probability values up to that upper limit. So if b is larger than a, then fb has a higher ceiling, higher upper value than fa, so it might have a larger value. It doesn't have to have, they might be equal as well, but it might have a larger value. Now, in this week's chapter, we are going to talk about discrete random variables, non-continuous, okay? Discrete. They have a countable number of possible outcomes. They might be infinitely countable, they might be infinite, but still they are countable. Now, for a discrete random variable, we will talk about the probability mass function, PMF. It's going to be PA, it's going to be shown as PA, but it's going to be defined as this equation. Now, PA, the PMF of A, the PMF of X in the value of A, is going to be, calculated with the probability that X is equal to A. Okay. Now, when we talk about X being equal to A, we can just give an example like this. Probability of when you roll a dice. Suppose that your X is the outcome of the dice. It's something, let's keep it simple. And I'll talk about, okay, what's the probability that X is 4? It's X coming up 4 in a roll of a dice, which is 1/6. Simple. Now, when you add all those values in the PMF, like we just tried to do in the previous example, it should give you 1, as you can see here. We are expecting to find 1 over there. Now, for example, let's start with a simple graph thing. So we have the PMF given us as this one. The probability of X being 0 is 1/4. The probability of X being 1 is 1/2. And the probability of X being equal to 2 is 1/4. Now, when you graph this, you will just get this little graphic. As you can see, these are the X values and these are its probabilities. Now, this can be also a bit more complicated. Think of a more complicated random variable. For example, let's say that we roll 2 dice and the sum of those 2 dice is the random variable X. Now, we get this, graph. As you can see here, the total of the 2 dice is shown in the bottom from 2 to 12. It cannot be 0 or 1, so these values don't have any probabilities at all. It can be 2 with a probability of 1/36. It can be 3 with a probability of 2/36, and etc. It's going up and then it's going down again. Now, we can graph the PMF easily in lots of different ways, but still the easiest way is just put the numbers, put the outcomes to the bottom and put the probability to the left-hand side and just use those values to graph it. Another example, let's say the probability mass function of a random variable X is given by Pi, which is equal to e to the power of minus lambda and minus lambda to the power of I and I factorial. Now, when you take a look at this one, this is actually something we are going to learn soon. This is a random variable with a name, but we don't know it. We don't know its name yet. So we're just seeing it for the first time. So we're just going to use it to calculate whatever it wants from us. It says that I goes from 0 to infinity. As you can see, there are infinitely many outcomes here, but they're all countable because you can count from 0 to infinity. Where lambda is some positive value. Yeah, lambda has to be positive. Okay, fine. The probability that X is equal to 0. Now, you can show this, you can also show this like this. P0, it's the same thing. Okay, but for this one, I cannot use a, notation like this, because it says that find the probability that x is greater than 2. But I already know that this means that 1 minus p x is less than or equal to 2. So from here I can actually write 1 minus p0 minus p1 minus p2. No, the p should be small but capital. So I can write this one as well instead of this one. And I already know the PMF, so I will just plug those numbers into the PMF and find the solution like this one. So what you have to do is just get the PMF and then use the numbers given to you and plug them in and find the values in there. As you can see, the probability that x is equal to 0 is going to be found from P0, which means that use 0 instead of I. So I put 0 instead of I, and lambda stays the same, so e to the power of minus lambda. Simple stuff. Now, let's just clear this one. What about cumulative distribution function? We already know what it was, but there's a relation between PMF and CDF. Now, cumulative distribution function can be expressed as a function of PA as the PMF. So think about it. When you're talking about FA, now the cumulative distribution function at the value at point A is, you're going to sum everything, every probability value up to and including A. So it's the same thing when you sum all the P values for A, using A instead of, X, you can sum up everything, and X is going to be summed up to the point of A. For example, when you're talking about F5, you say that, okay, if it starts from 0 and it goes to infinity, like the previous example, and when you're talking about F5, you are saying that sum P0, P1, P2, P3, P4, and P5, all of them summed together is going to give you F5. Okay, for example, if x has a probability mass function given by P1 is equal to 1 over 4, P2 is equal to 1 over 2, P3 is equal to 1 over 8, and P4 is equal to 1 over 8. Then its cumulative distribution function is given by, like this one. Why? Okay, the P1 is where it starts. Okay, the first probability we see with the least amount of outcome value. Okay, this is 1. 1 is less than 2, 3, and 4, so this is how we start. So before 1, any outcome has a probability of 0. So when you are coming up to 1, every value is a total of 0, because they're all 0, so their total, their sum is 0 as well. When you come to 5, it jumps to 1 over 4, because 1 has a probability of 1 over 4. So it's going to jump to 1 over 4 up until value 2, because when you come to 2, before you come to 2, there are no probabilities in there. No value has a probability. But when you come to 2, there's a 1 over 2 probability. So it's just going to jump from 1 over 4 to 3 over 4 at point 2. And then at point 3, you're going to jump to 1 over 8. And then add 1 over 8 and jump to 7 over 8. And at point 4, you're going to add another 1 over 8 and jump to 1 to the probability of 1. And after 4, there are no other outcomes as well. So it's going to stay at 1 anyway. And of course, it cannot be greater than 1 because their total should be 1. Now, this CDF, this graph, this function can also be graphed as like this one. As you can see, we have a dot here, which is field dot. It has a it's not empty. The inside of it is not empty. So it said that it's included here. And starting from 1 up to 2, which is not included in here because it's included at the top side. So in here, it's 1 over 4. This is the total probability, okay? And as you can see, from here, at the start, actually, this was 0. So if you say like this, it was here up until 1, okay? You can even take it from minus infinity. It's okay. It was 1, it was 0 anyway, up until 1. At 1, it jumps to 1 over 4. So 1 has a probability of 1 over 4. In 2, when you come to 2 at 2, it jumps to 3 over 4. So 2 has a probability of 3 over 4 over minus 1 over 4, 2 over 4, which is 1 over 2. At 3, it jumps to 7 over 8. So the jump is 1 over 8. So 0.3 has a probability of 1 over 8. And at 4, it jumps to 1 from 7 over 8. So the jump amount is 1 over 8 again. So 4 has a probability of 1 over 8 once more. And the expected value. Now, this one is going to be used from here till the end of the course, I guess. It actually has its own chapter in chapter 7 with lots of different applications and stuff, but still it has to be understood here. So it's actually very important and used a lot in exams as well. The expected value of x is a weighted average of the possible values x can take on, each value weighted by its respective probability. Now, it's an average, but it's a weighted average. We also call it mean. This weighted average is weighted by the probability values. Okay, this expected value can be defined and written as this equation. So this is the expected value of x. This can be read as pronounced as the expected value of x, and we are summing every multiplication of x with its respective probability value. So for example, take a look at this one. We know that x is 0 and 1. X can only have two values, 0 or 1. Okay, and the probability of x being 0 is 1 over 3, and the probability of x being 1 is 2 over 3. So the expected value is 0 times 1 over 3 plus 1 times 2 over 3, which is going to be found as 0.6, as you can see here. We have to calculate the probabilities and then multiply these probabilities with the outcome values and then sum them all together. For example, calculate the expected value of a roll of a die. Now, we know that the die has 6 different outcomes, 1, 2, 3, 4, 5, 6. All these 6 outcomes have the same probability, 1 over 6, 1 over 6, 1 over 6, 1 over 6. So all I have to do is multiply all these values with 1 over 6 and sum them up. So 1 times 1 over 6, 2 times 1 over 6, etc. The sum is going to give me 3.5. Now, something to note here. 3.5 is the expected value for that, x random variable, but it's not one of the outcomes in there. So there's no 3.5 outcome on a die roll. It's either 1, 2, 3, 4, or 5, or 6. So this expected value does not have to be in one of the outcomes. Okay, it doesn't have to be one of the outcomes. It can be. It can just come up like this, but it doesn't have to be. Okay, this is the mean value, the expected value. So, for example, a school bus of 120 students are driven in 3 buses. There are 36 students in one bus, 40 in another, and 44 in the third bus. When the buses arrive, one of the 120 students is chosen randomly. Now, we are picking a student at random, one out of 120. He or she can come from any one of the buses. Let x denote the number of students on the bus of that random chosen student. Find ex. Now, x is the number of students on a bus. Okay, what are the possible values of x? Which values can x take? Which values can x take? 36, 40, and 44, because those are the values of the buses, number of students on the bus. So it can take 3 different values, 36, 40, and 44. Now, out of these 3 values, they all have different, probabilities of being picked. Why? For example, if you're going to pick a student from the 36 student bus, you have a probability of picking that student 36 out of 120. So 36 over 120. If you're going to pick a student from the 40 student bus, then you have a probability of 40 over 120. If you're going to pick a student from 44 student bus, then you will have a probability of picking him 44 out of 120. Now, I have the x values, the outcome values, and I have the probabilities. I will just sum them together after multiplying them. So as you can see, 36 times 36 over 120, etc. When it's all summed, we get a value of 40.26. It's not 40, it's 40.26. Because it's asking us to pick a student, not pick a bus. If it had told us to pick a bus at random, then all these numbers would have a probability of 1 over 3. Which is different from these values, as you can see. And it would have a x-value value of 40, because it's just going to be the average of all 3 values. But in here, we are picking a student, which is a different value than picking a bus, different probability value than picking a bus. Now, expectation of a function of a random variable. This is actually a very important, part of the expectation. because it's going to give us a very handy shortcut for lots of different calculations. Now, for example, we know how to compute EX now. Just multiply the probability value with the X value, then sum them all. It's easy, okay? How about GX? Now, we have a function of X. We have to find the mean or the average of, or the weighted average or the expectation of that function of X. Now, in here, we start with a simple problem. We have an X random variable which can take values of -1, 0, and 1 with those probabilities 0.2, 0.5, and 0.3 once again. Now, it wants us to compute X square. Now, X square is a function of X. It's a function of the random variable. So I will just define X square as Y, a new random variable. Now, I know that Y can take two values only, 0 and 1, because X could take three values, -1, 0, and 1. X squared takes two values, because 1 from here, 1 from here, and 0 from here. So these two are the same for X squared. So my probability of being 1 for Y becomes 0.5, because I add these two. And my probability of Y being equal to 0 is once again 0.5, because it comes from here. So my expectation of Y, now this here is going to be calculated from X squared anyway. This Y is just, think about it. I have two outcomes, 1 and 0, and both have 0.5 probabilities. I will just multiply those outcomes with those probabilities and then sum them. So I have 0.5 times 1 plus 0.5 times 0, which is equal to 0.5. But that's not easy all the time. That's not that easy all the time. We need something more concrete, something more mathematical. It comes from here. Instead of calculating them one by one like that, we can just use this formulation. Now, expected value of Gx is equal to Gx times Px summed together. Now, this is actually like writing this. Let's just write it. Remember this one. Ex was equal to sum of x times Px. Now, these are the same thing. The main difference is instead of x, we are writing Gx, the function of x. Okay? Instead of x, we are writing Gx over here. So this one is fundamentally the same thing. We're just writing the function instead of x. This side is going to go all the time. Now, the proof is easy, but you don't have to know it, but you can just check to see how it goes there. But, you need to know this part. This is more important than that one, the proof. So as long as you can use this formula, you're okay with it. Let's see how it goes. A product sold seasonally yields a net profit of $B per unit sold and a net loss of L per unit left unsold when the season ends. So I have a stock, I have a demand. I'm just trying to find out how much I will sell. But here, you can take a look at this one. A net profit of $B per unit sold. So as long as I sell something, I get $B, okay? And a net loss of L per unit left unsold. If I don't sell it, it stays in my inventory, so this is an inventory cost and value of L. Okay, let X the number of units of the product ordered during any season. This is the demand, okay? The X, which is a mass function of Pi. Okay, it has a probability. It can be either 1, 2, or 3, or 4, or 5, or etc. I don't know the PMF right now, but it can be any value that PMF allows. So, if the store must stock this product in advance, find the expected profit in its simplest form. Expected profit. So, I have a demand here, which is X, and I have to stock something, which I'm going to call S. So, I have to pick the amount of S so that I know how much profit I can make. Okay, let's assume that S is less than or greater, one of them, X. So, when S is greater than X, my demand is less than my supply. Okay, so I will have some inventory left, and this inventory will cost me. I will sell for every demand, okay, the demand will be met, but the leftover parts will be subtracted from my profit, because they're going to be a cost, inventory cost. On the other hand, in the other version of this one, X can be greater than S. The demand can be greater than the stock or the supply. Now, if the demand is greater, I will sell everything in my stock, and that's it. I won't have anything else to sell, so some of my demand will be unmet. Some of my customers will not get what they want. Okay, but still, these two scenarios can be calculated differently. In the first scenario, I'm gonna sell everything. Okay, every demand will be met. So X units will be sold for B, for a price of B. Bx is my income. But after that one, I have some leftovers, S minus X. These leftovers are going to cost me L each, the inventory cost. So S minus X times L. This amount will be subtracted from my income, which will give me the net profit. On the second scenario, my demand is less than my greater than my supply, so I will sell everything in my supply, which is the amount of S. Okay, so I will sell each of them for B, so B times S is going to be my income for the second scenario. Now, as you can see, these two are written like this. Now, this is my profit. So I'm going to find the expected profit, which is going to be expected value of this one. So what I have to do is just take this one and plug it into the expected value function. Now start with the first one, this part where X is less than S. Now I know that when X is less than S, I'm going to have to take the X value from 0 to S and get all the probability values multiplied by them and then sum them. Now I know that this is my function. The gx part is this one. Now I will just put gx over here, this function over here, and I'm going to put pi, which is my PMF. This is when I, which is for us the S value actually, X value actually, when I is less than S. It can be equal to or less than X. So I'm going to just find for all I values. And then I have I is greater than S, but it's going to start at S plus 1 because this is discrete, so all the jumpings, all the steps are one step ahead, just one. They have a length of 1. So instead of S, we're going to start with S plus 1, which is going to go to infinity. Now this here, SB, is my profit when X is greater than S. So this is where X is greater than S. As you can see, I start with S plus 1 and goes to infinity. So this is going to be the expected value for the second scenario. When you sum these two, you're going to get the expected value. But you have to simplify them first. Open up the parentheses, just get rid of the excess stuff, and then sum it up to this one. Okay, this is the simplest form we can get. So corollary. This is actually a useful corollary, which is going to be, you're going to be using this one a lot, especially with expected value problems. It says that the expected value of AX plus B is equal to expected value of X multiplied by A plus B. Now, this is a bit intuitive, but as you can see, there's an easy proof here as well. You can just plug in these values into the equation, the definition actually, and then get the value out of there. Now, this corollary is actually useful, very useful, and it's going to be useful with variance as well. There's a similar corollary in there, we will see. And what's variance then? Variance is the, let's say, the spread, but the length that you are away from your average, from your expected value. It's the, how many different values you have that are away from your, let's say, average value. The spread is the most common use, definition for it, but still, the easiest way to understand variance is just take a look at this, graph. As you can see, we have two different variables here, the black, the blue, and the red one. They both have the same average. They both have the same, weighted average, the same expected value, which is 100. But the blue one has a greater variance. Standard deviation here is the, let's say, standard deviation and variance is the root and the, let's just say standard deviation is the root of the variance. So you can just say that you have to, find the variance by taking the square of the standard deviation. As the standard deviation here is a bit smaller than the standard deviation of here, it has a less spread. So as you can see, with the red one, you have less spread. It's more, compact. It's more together. With the blue one, as it has a higher value of standard deviation, it's greater. It's spread over the board much more. So the variance is defined as sigma square, or as the expectation of the square of x minus mu. Mu is your mean or expected value for x. So these two values, mu and sigma, are going to be used a lot. Mu is your expected value for x, sigma is your standard deviation, sigma square is your variance. All right. Now we know that variance has to be non-negative, because variance is actually a measure of distance, you can say, because it's looking at how far apart from your mean you are, your expected value you are. So it's a distance thing. And of course, it's a square, so, sigma square, so it has to be non-negative. But the definition of variance, this formula, isn't used that much in that regard. So we prefer using this one most of the time, as long as it's available and it can be readily used easily. The thing is, in this formula here, we are looking for two things. The first one is the expected value of the x square, which is a bit harder to calculate. And the second one is the square of the expected value of x, which is easy because we most of the time know how to calculate the expected value of x with a formula most of the time. Not always, of course, but still it's a bit easier when compared to the first term. Now, using these two, we can calculate the variance value. For example, calculate the variance of the roll of a fair dice. Now, we know that the expected value of a roll of a fair dice is 2.5, 7/2. So the square of the expected value of x, which is e square x, 49/4, which is easy because we're just taking the square of 7/2. But the other one, the x square, expected of x square, needs a bit more calculation. But it's not that hard in this case because we know that the x values are 1, 2, 3, 4, 5, 6. So we just take the squares of them, 1, 2, 1, 4, 9, etc., and then multiply that with 1/6, and now we get 2.91. Now this is the variance. If we were looking for the standard deviation, we would just be looking for the square root of this value. And then there is the corollary that I had told, in expected value. This is the same thing with a slight difference. Now we are looking for the variance of ax plus b. Now in here, b is removed. Okay, b is removed, and a is going out as a square. There's a perfectly, well explanation for this mathematically. But let's just take a look at the, let's go back and take a look at the graph now. In this graph, remember, we said that this red one has a smaller variance and the blue one has a larger variance, greater variance. Okay. Also, I can say that if I take every value in this red, one and add 5 to them, for example, add 5 to every value here, my average will become 105. It will just move. Okay. But the shape won't change. Okay. The shape will still be the same thing, but it will just move. The shape will just move along the axis. Okay. So as the shape doesn't change, the variance will not change as well. So moving the shape doesn't change the variance because the distance from the mean, the expected value, is going to be the same. So in that regard, we know that moving is like adding a b, adding a value to x, and this moving is unimportant. So it's not going to be effective when calculating the variance. This a is going to come out as a square because variance has, is related to the square of the expected value. So when there's an a, it's going to come out as a square. You can see how it's done, how it's proven mathematically down here, but you don't have to memorize it as usual. But taking a look at this one might be, helpful for, as an exercise. So standard deviation, this is the square root of variance, and it's shown with the sigma. variance is shown with sigma square, standard deviation is shown with the sigma, and this is the exact units of distance from the mean. You can say it's easier to understand when you are using this alongside the data you have, but still it's the same amount of. For example, if all the data is in centimeters, for example, some sort of outcome is measured in centimeters, then the standard deviation is in centimeters as well. Okay. And we have the discrete uniform distribution. Now, this is the first named distribution we will see. Distributions, some special distributions exist and they have names, and their expected values and variances are calculated with simple formulas, so you don't need to calculate them all the time again and again and again. So the first one is the most simple one, uniform distribution, discrete uniform distribution. In this one, in the discrete uniform distribution, it's a symmetric distribution, and there's a finite number of values. Okay, we can just find the number of values. It's finite. It can be 10, 20, etc. Any number n, which is not infinite. So they all have those n values all have the same probability, 1 over n. Now, for example, fair die, roll of a fair die. The number of outcomes is 6. You have 1 to 6, and they all have the probability 1 over 6. So it's a uniform distribution. Now, the uniform distribution is shown like this from A to B. It has a lower limit and an upper limit. It can be anything from minus 20 to plus 20 or anything larger or smaller. It doesn't have to be in the negatives. It can be all positives as well, or it can be all negatives as well. As long as it's not infinite, it's okay. Now, from A to B, this discrete uniform is, we can calculate its expected value with this formula, of course, using the expected value formulation. But this one just gets, simplified into A plus B over 2. What you do is just take the average of the, top and bottom values. That's it. It's always like that. So it's the same with the roll of a dice. 1 plus 6 over 2 is 7 over 2, which is the expected value anyway. So when you have a discrete uniform distribution, you can just use A plus B over 2 to find this mean. You don't need to calculate it again and again and again using the expected value formula. You don't need that one. Now, the Banel trial. The Banel trial is extremely important because it takes part in lots of different variables. The first and foremost one is the binomial random variable, but it's inside lots of random variables. You'll see the Banel trial is just a simple experiment where there are only 2 outcomes: success or failure. Now, this sounds like an easy thing, but think of it like this: it doesn't have to be 2 outcomes per se. It just has to be refined into 2 outcomes. For example, roll of a die can be a Banel trial. How? It has 6 outcomes. But I can just say that, okay, I'm rolling a die, and I will consider it a success if the die is 3 or greater, shows 3 or greater. Now, I have just broken the sample space into 2 parts: a success part and a failure part. In the success part, I have 3, 4, 5, and 6, the outcomes, those 4 outcomes. In the failure part, I have 1 and 2, those 2 outcomes. So my success probability is 4 over 6, and my failure probability is 2 over 6. So I can just assign some outcomes to the success part and some to the failure part and find probabilities from there for success and failure. For Banel trial, we'll just say that, okay, we will say that P0 is failure, P1 is success, and P value is the success rate. Okay, probability that we find a success for each trial, and they all have the same probability. All the trials are independent and they have to have the same probability. It's important. The same probability part is important because if they don't have the same probability, then it's not a Banel trial. It just becomes something else. Now, for each trial, we also have, of course, a failure rate of 1 minus P. But when we talk about P, we infer 1 minus P anyway. It's just in there, we know it. So the binomial random variables, the first random variable that Banel trial will be used in. We have already seen this one. We have already talked about this one. We didn't name it, but we have seen examples of it. So we have n independent trials. Those trials have a success probability of P and a failure probability of 1 minus P, like a Banel trial. They're all Banel trials anyway. And X represents the number of successes that occur in n trials. So we are making, we are having an experiment, making some trials, and we count up to n times. We make n trials, and out of these n trials, we are looking for the number of successes, which we're going to name x, the random variable x. So this x is a binary random variable. Okay, it has two outcomes: failure or success. It's counted through lots of different trials. So we are trying to find the number of successes. This is the binary random variable, and it's shown with parameters n and p. N is the number of trials we are making, and p is the success rate, the probability of success. Those two parameters are enough to talk about a binary random variable. Then we have the third value, the I, the number of successes we are looking for. How many successes do we want? This is the I value. Okay. So as you can see, this formula, this is the PMF, the probability mass function. Every outcome is shown here. The probability of every outcome is shown here. Okay. As you can see, for I from 0 to n, you can find all the values in here. So n choose I. We are choosing the I trials that will be successful out of those n trials. P to the power of I. So we know that we have I successes. They each have a success probability of P. So P times P times P times P till we get I of them together. And now we have 1 minus P to the power of n minus I. In here, we know that these are the failures. So this is the failure rate, the probability of failure, and the number of failures. So this totally gives us the PMF, the probability of any I value. The I here is, of course, number of successes. So in the graph on the right-hand side, right bottom side, you can see three different binary random variables. One of them, the blue one, has a success rate of 0.5 and a trial number of 20. The green one has a success rate of 0.7 and a trial number of 20. The red one has a success rate of 0.5 and a trial number of 40. Now, you can see how number of trials and the success rate changes the graph. For example, let's start with comparing blue and green. They both have the same number of trials, 20. But the green one has a higher success rate. So the higher success rate yields more probable successes, more successes on the right hand side. So as you can see, for example, with the blue one, getting a success number of 10 has about a probability of 0.18, and then it drops. Okay, this is the most one we can get, 0.18. But with the green one, we have 14 here. Top point is 14, and this one has a probability of 0.20. Much more successes with much higher probability. So when P grows, the graph goes a bit to the right hand side and goes up. On the other hand, let's just compare blue and red now. The blue one and the red one have the same probability, same success rate, 0.5, but the number of trials is greater in the red one. Now, in here, the red one just goes along to the right-hand side, grows to the right-hand side more and more, and just drops a bit. This drops because the total should be 1 anyway, so this is expected because the number of successes growing, because there are there can be 21, 22, 23, etc. successes which weren't in the blue one, but the total number is growing, but their respective probabilities are going a bit shorter, it seems. As you can see, this blue one ends at 20, the red one ends at 40, and the total number, the total of the sum of all those 40 probabilities should be equal to the sum of all those blue probabilities, which is going to be 1. That's why just making more and more trials spreads out the probabilities even more. A simple question. It is known that screws produced by a certain company will be defective with probability 0.01. So we have 1% chance of creating a defective screw, independent of each other. The company sells the screws in packages of 10 and offers a money-back guarantee that at most one of the 10 screws is defective. Okay, what proportion of packages sold must the company replace? So we are looking for the probability of finding more than one screw. Okay, more than one screw defective in that 10 screw box. So what we need to do is just find the complementary of it, because when you're talking about finding more than one screw defective, you're talking about 2, 3, 4, 5, 6, 7, 8, 9, and 10. 9 different solutions. No, I don't want to go in there. Instead, I'm just going to find the number, the probability that the defective number of screws is 0 or 1, because it's just two calculations, and I'll just subtract that from 1, and that will be the probability we are looking for. So what we need to find is the probability that there are no defective screws inside that batch, and there is one defective screw inside that batch as well. For no defective screws, now here we are going to use binomial random variable, and we are going to have to talk about the success and success rate. In here, success is finding a defective screw. So it's a bit counterintuitive. Okay, finding something bad is a success. It shouldn't be, but it is. You can just assume which one is a success and which one is a failure as you like. Okay, I'm just comfortable with using this defective, finding this defective screw as a success. But I could have said it's a failure and calculate from there as well. It's the same thing. It's just changing the sets. Okay, you can say that, okay, this is a failure, this is a success set. Okay, I'm just going to switch them. It's still the same thing. I can find I have to just word the question a bit differently, but I'm just going to be looking for the same probability anyway. So let's just say that finding a defective screw is a success. So my success rate, my probability of success is given to me here, 0.01. This is my p value. My n, number of trials, is given here, packages of 10. So n is 10, p is 0.01. And I have the value of I as 0. No successes, okay? No defectives in there. So I'm just going to use 10 choose 0, because I'm going to choose 0, success out of 10 trials. And I'm going to say 0.01 to the power of 0 and 0.99 to the power of 9. No, sorry, 10. This is going to give me the probability that there are no defective screws in there, which is like 0.90. And then I'm going to look for the scenario where there's one screw that's broken, that's defective. And that's the probability that x is equal to 1. So I'm going to have to choose one screw out of 10, which I have done, 10 choose 1. Then I will say that that screw is broken, it's defective, so 0.01 to the power of 1. And the rest 9 are not defective, they are failures, so 0.99 to the power of 9, which is going to give me 0.09. Now, these two are the things that I want, that are not going to be replaced. The number of packages that's going to be replaced. But I want the opposite of it, of course, right now. What proportion of packages sold must the company replace? So I have to subtract these two values from 1 to get the probability that any box is replaced. So 4 in 1,000 boxes, 4 boxes in 1,000 boxes are going to be replaced. This is what the answer is telling us right now. What about this one? This might be a bit more familiar because it's a biology question actually, and I'm pretty sure you have seen these in high school, I guess, but we'll see. Suppose that a particular trait, such as eye color, left-handedness, hair color, etc., of a person is classified on the basis of one pair of genes. Okay, and suppose also that D represents a dominant gene and R is a recessive gene. Thus, a person with DD genes is purely dominant. One with RR is purely recessive, and one with RD is hybrid. The purely dominant and the hybrid individuals are alike in appearance. Children receive one gene from each parent. If with respect to a particular trait, 2 hybrid parents have a total of 4 children, what's the probability that 3 of the 4 children have the outward appearance of the dominant gene? Now, this is a mouthful. Yes, this is a story question. It's long and it's lots of things to be, careful about. First of all, we should understand that this is a binomial random variable question, but we'll understand how to catch it in a second. Now, here we have genes and 2 parents, a mother and a father, creates a new gene. So, for example, if both of the mother and the father, they are both dominant, types, they have 2 D genes, so the child should be DD again. Okay, but in here we have 2, let's just say, an R and a D here, and an R and a D here. So both of the parents are hybrid. So the kids will be either RR, DD, RD, or DR, depending on which one gives which one. So when you take a look at it, RR, DD, RD, DR. And from here we can see that it says that we want the outward appearance of dominant gene. And it also says that hybrid individuals are alike in appearance with the dominant ones. So these three over here, DD, RD, and DR, are what we are looking for. Now, this has a probability of 3 over 4, which is 0.75. This is my success rate. This is my p-value now. My success rate is 0.75, 3 over 4. And my number of trials, N, is 4. They have 4 children. And they want, they're asking the probability that 3 of them have that appearance. So I is 3. So I have the numbers already. P is 0.75, N is 4, and I is 3. All I have to do is just plug these into the equation, and we're done. And so we're just gonna plug them in like this, and we get 0.42. We're done. So this is actually, knowing how to, use that story and get those, important values, the number of trials, the number of successes we are looking for, and the success rate, those three. Just getting those three out of this story is the most important part, especially for binomial random variable. So properties of the binomial random variables. There are a few things that we need to see or know about it. The first one is the expected value. It's extremely easy. Mu, we know what mu is, but in the binomial random variable, it's n times p. So multiplying the number of trials with the success rate gives you the expected value of that random variable. Simple as that. NP is the expected value. For the variance, you get NP times 1 minus p. So you need to have the number of trials, success rate, and failure rate together multiplied. It's going to give you the sigma squared. You can take the square root of this one to get sigma alone, of course. And the CDF is just summing them all. You know that already. What about the Poisson random variables? Now, first things first, this is not Poisson or Poisson or something like this. Poisson is French. So as far as I know, that's how I was taught. It's pronounced as Poisson. A random variable X is a Poisson random variable with parameter lambda if it takes on the following PMF values. Now, as I said at the start of the course, this is a random variable that we know of. Okay, we have seen this formula, and this is the Poisson random variable formula. Now, as you can see here, we have E, we have lambda, and we have I. I is the number we are looking for, okay? The number we are, the probability that the number we are looking for, and lambdas are the parameters. So if you graph this, oh, by the way, this random variable has infinitely many outcomes. So it can start, it starts as 0 and it goes to plus infinity. So as you can see, for different lambda values, this function has different graphs. For example, for lambda is equal to 1, it goes down like this. For lambda is equal to 4, it goes up a bit, then goes down to infinity. For lambda is equal to 10, it goes up a bit and then starts going down. So as lambda grows, your route to up, your route to the top side is going to be further and further away, as you can see from here. But it's not, the graph part is not our concern right now. We're going to be using this one extensively, not the graph, but the formula, the function extensively anyways. Now, suppose that the number of errors on a page has a Poisson distribution with parameter lambda is equal to 1 over 2. Calculate the probability there is at least one error on a given page. At least one error, okay? It can be 1, 2, 3, 4, 5, 6, 7, infinitely many. I don't want to, take all of them and just sum them all one by one. So what I have to do is just find the probability of no error, 0 errors, and then subtract it from 1. Okay, the probability of no errors is going to be fine with x is equal to 0. So my I value for this question is 0. I already know my lambda value 1 over 2, so I'll just plug in 0 and lambda 2 into this formula, and then I will get this one. And I'll subtract it from 1, as you can see here, and I will get 0.39. This is an easy question. With the Poisson random variable, we have similar, let's say, expected value and variance calculation modes, but it's extremely easy this way. We have only one parameter, so that parameter is used for expected value and variance. And for the Poisson random variable, they are equal. So both expected value and the variance is equal to lambda. That's it. You don't need to know anything else about that part. You can, of course, always try to get to, find the expected value and variance formulations, use the definitions to find those values. But it's good math. You have to check it out. But I don't know if you will. We'll see. So what do we use? What do we need them for? Or how do we use them for, instead of each other? There is a problem with binomial random variable. What kind of problem? The thing is, with binomial random variable, when numbers get too large, you stop being able to calculate stuff. For example, think about it. Let's assume that there are, 50,000 items, and you are looking for 500 defectives, with each defective having a probability of 0.01. Okay, so 50,000, choose 500. Wow. This combination, that's not a combination you can calculate easily. It's going to be a huge answer. 50,000 out of 500 out of 50,000. It's going to be a huge number. And then add more. 0.01 to the power of 500, 0.99 to the power of 49,500. Nope, not going to deal with it. It's too large. Okay, it's not easily calculable. So you have to do something else. You have to, drop binomial and use something else to calculate that one. This is what Poisson comes in. Now, for n large enough and p small enough, those enough values are debatable, but still, it's easy to see how it goes on. We can say that Poisson looks like binomial. For example, take a look at this value again. The lambda value again. As you can see, this shape looks like the binomial random variable shape. It had the same shape as well. Okay, so we can say that we can use one of them instead of the other one. But to do this, we have to make sure that there are a few important parts. We have to calculate the lambda, and the lambda is calculated from NP. Why? Because the expected value is lambda, and the expected value is NP anyways. But lambda is also calculated from variance, which is NP 1 minus P. Now, this 1 minus P makes the lambda, changes lambda. It makes it something else, something different. If P is small enough, this value is going to be close to 1. So this lambda will be very close to this lambda, which is going to be, easy to calculate. If P is not close to 1, the variance won't hold, won't be the same. You can still apply this technique. You can still find an approximation, but you cannot be sure that the approximation is close enough in that regard. As long as the P is small enough, this one is close to 1. So this NP value is equal to this NP value anyway. So this lambda will be very close to this lambda. But if you cannot find a small enough P, it's going to be a bit more tricky, let's say. Okay, how do we do that? For example, suppose that the probability of an item produced by a certain machine will be defective is 0.1. Find the probability that a sample of 10 items will contain at most one defective item. Now, this can be done with binomial random variable. The numbers aren't that large, so we're going to use that one first. But still, for binomial random variable, we are looking for at most one defective item. So I have to find 0 and 1, two different calculations. 0 defective items plus 1 defective item. Now, for 0 defective items, I have to choose 0 out of 10. And then I have 0.1 to the power of 0 and 0.9 to the power of 10. It's going to give me the probability of having 0 defective items. For 1 defective item, I'm going to choose 1 out of 10. And then I have to calculate 0.1 to the power of 1 and 0.9 to the power of 9 as well. This one is going to give me 0.7361. Now, this is the exact solution. Okay, the exact solution, but it's got a long tail, because think about it. You are going to find the value of 10th power of 0.9, which is, at least 10, maybe more decimals there. So in here, 7361. This is my exact solution, almost exact solution. For the other part, for Poisson approximation, I have to find the lambda value. Now, the lambda value, which is also the expected value, is calculated with NP. The N value here is 10, and the P value here is 0.1. So NP is going to give me 1. So my lambda is 1. And using that lambda, using that 1 value, I'm going to have to find at most 1 defective item. So I can just calculate the 0 defective and 1 defective once again, and then sum them. So that's what we do here. As you can see, lambda is equal to 1. So A is very e to the power of minus 1, and 1 to the power of 0 and 0 factorial. This part is 1 anyway, this part is 1 anyway, so e to the power of minus 1 and e to the power of minus 1, they are summed together, 2 times e to the power of minus 1, which is going to give us 7358, which is very close to the exact solution. It's almost the same. So as long as it's not an extremely important and extremely sensitive calculation, this approximation gives us a good approximation. Now, this approximation method gives a good solution. That's really close to the exact solution. Another usage of Poisson random variables, this is something about time. When we're talking about time, we are usually talking about the Poisson random variable or the exponential, but we're going to see it next week, not this week. So in this one here, suppose that earthquakes occur in Istanbul with parameter lambda is equal to 2 and 1 week as the unit of time. So there are 2 earthquakes per week, which can be scaled to 4 earthquakes per 2 weeks, 10 earthquakes per 5 weeks, etc. So from here, it asks us to find the probability that at least 3 earthquakes occur during the next 2 weeks. Now, 3 earthquakes in 2 weeks. I already know that for 2 weeks we have a mean of 4 because it already says us for 1 week it's 2. So for 2 weeks it's 4. So I'm trying to find that the number of earthquakes is greater than or equal to 3 for 2 weeks, which I can write as this one. Now, I'm not going to look for all the possible earthquakes from 3 to 4 to 5 to 6, etc. to infinity. Instead, I'm going to look for the complementary 0 earthquake, 1 earthquake, and 2 earthquakes, and I'm going to sum them up together, and I'm going to remove it from 1, subtract it from 1. As you can see here, there is 2. This is the 2 week notation for 2 weeks. 0 earthquakes in 2 weeks. 1 earthquake in 2 weeks, 2 earthquakes in 2 weeks. Those are the probabilities. I also know that lambda is 4, so I is 0. Add 0 and 4, and you get this one. Lambda is 4, I is 1, you get this one. Lambda is 0, lambda is 4, sorry, n is 2, you get this one. So from these 3, you get 0.76. When you subtract them from 1, you get 0.76 probability for 3 earthquakes during the next 2 weeks. The second part is much harder, let's say. Find the probability distribution of time. Okay, it's asking us to find the CDF, the probability distribution of the time, starting from now until the next earthquake. Now, this is finding the distribution of some random variable, okay? So we have to denote a random variable, which is going to be x, the amount of time in weeks until the next earthquake. So if it is 0, the earthquake is happening now. If it's 1, it's going to happen in 1 week, after 1 week. And if it's 2, it's going to happen in 2 weeks, etc., etc. Now, this x, okay, we are looking for the CDF of this x. The CDF means, the cumulative distribution function means, as you remember, having an upper limit for that x value. So I'm just going to write it like this. Let me just show you. This is what we are looking for. X is greater than t. Okay, the cumulative distribution of x. X is greater than t. Sorry, smaller than t. Less than or equal than. Okay, t. Now, to find this one, we can use its complementary. 1 minus x is greater than t. Now, when you talk about x is greater than t, you're actually talking about this part, because we had used this one to calculate this one anyway. Now, in here, we are looking for 0 earthquakes. Okay, why 0 earthquakes? Because we need to make sure that there are no earthquakes till week t. Okay, this one is 0 is greater than t, means that you don't have any earthquakes in the first t weeks. Okay, the first earthquake is after week t. So we are looking for the probability that the number of earthquakes in the first t weeks is 0. So this one becomes this one. This transformation is the most important part. If you can think of this transformation, if you can understand it right now, it becomes very easy. This says that, remember, x is the number of weeks until the next earthquake. And it says that x is greater than t. This means that in the first t weeks, there are no earthquakes. Okay, so this is how I can write it as well. I already know how this is calculated, because I have done this here, as you can see. But the difference is this is t weeks instead of 2 weeks. So I will just write t, the value t, instead of 2, which will give me, when subtract from 1 minus e to the power of minus 2t. Is that okay? All right. Now, geometric random variable is yet another random variable that we are going to use. And this one is a bit tricky. Not that much tricky, but just a bit tricky. Now, in here, in geometric random variable, we are again talking about trials, but we perform these trials till we get the first success. When you succeed the first time, you stop. Okay, this is simple enough. So this means that we have a probability of P of success, a Bernoulli trial once again. And in this geometric random variable, you keep going and going and going till you find that P, so you succeed one time. That's it. Now, to do that, you have to fail, I don't know, n minus 1 times, if the total number of trials is n. So you have to fail n minus 1 times, which is going to give you this one, 1 minus P to the power of n minus n. And then multiply with t, because your last trial is going to be a success. This is your PMF, okay? PMF for geometric random variable. Now, the expected value is 1 over P, and the variance is 1 minus P to the over P square. Now, these two are important as well, especially the expected values, because you can find some shortcuts using those expected values anyway. If you can understand that the question you are given has a specific random variable, like a geometric random variable, etc., you can just write it. This is geometric random variable, and this is the expected value is 1 over P, so you don't have to calculate the expected value again and again and again. Example 13. This is with the geometric random variable, of course. An array contains W white and B black balls. Balls are randomly selected one at a time until a black one is obtained. Okay, we are picking balls one by one. If we assume that each selected ball is replaced before the next one is drawn, this is important because if I don't replace it, the probability changes, so I cannot have a Bernoulli trial because they are all different Bernoulli trials, so they don't have the same success rate. If I just take it out and don't replace it back in, don't put it back in, they're just random trials. What's the probability that exactly n rows are needed? Now think about it like this. We are picking them one by one until we pick a black one. Okay, the first one is white. Replace it back. Again white. Replace it back. Black. And we're done. Now, exactly n rows. This means that n minus 1 rows are all white. The nth row is black. So I have to calculate the probability for n minus 1 white rows, this one, and 1 black row, this one. So you get this one. What about at least k rows are needed? Now, when you say at least k rows, it says that the first k minus 1 trials are failure. So you have to make sure that they don't succeed. So you have to have k minus 1 failures, which is 1 minus P to the power of k minus 1. And P was W over W plus P. Black over black plus white, of course, but still 1 minus P part is like this, W over W plus P. Now, this one gives you the probability that you are looking for. Now we have negative binomial random variable. Now, with negative binomial random variables, the name suggests something to do with binomial random variable, but still it's a bit different. It's a mixture of geometric and binomial, let's say. We are looking for R successes, okay? We are going to keep doing trials until we gather R successes. Now, with geometric random variable, we are looking for just one success and we would stop there. With negative binomial, we are looking for R successes. So the last trial is going to be a success, that's for sure. But anything before the last trial can be success or failure. But it has to have R minus 1 successes because the last one is a success for a total of R successes. So excluding the last trial, we can think of this as a normal, as a binomial random variable, excluding the last one though. If you exclude the last trial, you have n minus 1 trials with R minus 1 successes. It's the definition of binomial random variable. So you just write the formula for binomial random variable like this one. N minus 1 choose R minus 1. and p to the power of r minus 1, and 1 minus p to the power of n minus r. Now, here, this one, up to here at least, this one, is going to give us the probability for picking, for getting r minus 1 successes in n minus 1 trials. The last one, though, this one, is just p, because it's the last trial and it's going to be a success. So it has a probability of p. So this one is our PMF. This huge formula is our PMF right now. From here, we can just find the expected value, which is going to be r over p. As you can see, with geometric random variable, it was 1 over p. Now we are looking for r different success instead of 1 success, so it's r over p. It's very relatable. And the variance is r times 1 minus p to the over p squared, which is the same except with the r part, of course, with geometric random variable. So this is negative binomial. We can see lots of different, applications of this one as well. I would advise you to check the book so you can see, the problems in there. And another random variable is a hypergeometric random variable. Now this one is familiar because we have been using this one from the second week. Okay, since the second week we have been using this one because we already know how to use this one. So, for example, this is the choosing random variable. We have a size n, which is going to be chosen from n balls, capital N balls. So W of them are white, B of them are black. So X is the number of white balls selected. All right, up to here, it's okay. So the probability that X is equal to I, number of white balls, for example, 3, 4, 5, whatever, number of white balls. So we're just gonna pick those. I balls out of W white balls, N minus I balls out of B black balls, and the sample space, N out of N. So this one is something we are already using. We have used it in here in this week as well. We use it all the time. We know what it is. We're just naming it, the hypergeometric random variable. This is it. This is the name. So how do we use it? Let's just remember. A purchase of electrical components buys them in lots of size 10. It is policy to inspect three components randomly from the lot and to accept the lot only if all three are non-defective. If 30% of the lots have 4 defective components and 70% have only 1, what proportion of lots does the purchaser reject? Okay, we are looking for the amount we reject. We can find it from, the inverse of, or from the complementary of the amount we accept. So to accept it, we need to make sure that there is either 0 defective item or just 1 defective item. And we have 2 different types of boxes. One of the boxes have 4 defective items and the other one has just 1 defective item. Okay, so to find the probability that there is only, 1 or there is no defective item, not one, but no defective item, we have to just calculate the probabilities using the hypergeometric random variable. For example, as you can see here, in this one, we first pick the 4 defective box, okay, with probability of 30%, 3 over 10. We are picking the 4 item defective box. In here, we pick 0 defective items and then pick 3 non-defective items. So, oh, sorry, this one says that there will be no defectives. Okay, not one defective, but no defective at all. I mixed up the question, sorry. But still, in here, as you can see, we want to find all 3 picks are non-defective. So we are looking for 0 defective items, which here corresponds to 0 items out of 4 items, 3 items out of 6 items. These are the non-defective ones, the working ones. And this 3 out of 10 is the sample space. So this one is picking 0 defective from 4 item, from a box where 4 items are defective. And this is the probability of choosing that box. As you can see, it's 30% of the lot has 4 defective items. And here we have picked the box with 1 defective item only, with 70% probability. And from that 1 defective item, we are not picking anything out of it. We are 1 choose 0. And from 9 working non-defective items, we are choosing 3 of them, 9 choose 3. And the total sample space is 10 choose 3 again. So summing those two, we get 0.54. This is being successful, okay? This probability is not rejecting. This is accepting the box. Okay, so 1 minus this means it's rejecting the box. So instead of this one, we use this one. 1 minus PA is rejecting. 1 minus accept is rejecting, which is 0.46. So 46% of the boxes are rejected by this guy, okay, this purchaser. So all the exam questions. Exercise 1. Suppose that the distribution function of x is given by, there's a distribution function here. This is a bit skewed, it's slanted, so you can just try to understand it. But the f is the cumulative distribution value is 0 for any value less than 0 of b. It's b over 4 when b is between 0 and 1. It's 1 over 2 plus b minus 1 over 4 when b is between 1 and 2. It's 11 over 12 when b is between 2 and 3. And it's 1 when b is greater than 3. Now, as you can see, these are our CDF values, okay? It wants us to find the probabilities of 1, 2, and 3, x being equal to 1, 2, and 3. So, to find the probability that x is equal to 1, we have to check if there's a jump, if there's a difference in the cumulative distribution function graph at point 1. Now, let's see. For 1, we have two different formulas, okay? The first one is b over 4, where you are coming to 1 from the left side, the limit on the left side. And the other one is 1 over 2 when you're coming from the right side. So there's a difference, there's a jump there. Okay, so this jump gives us the value 1 over 2, right? No, 1 over 4. So 1 over 4, 2 minus 1 over 4 is 1 over 4. So the probability of x is being equal to 1 is 1 over 4. Then we're going to have to check x equal to 2. The probability of x is equal to 2. I'm going to check the, point 2 from right and left side once again. From the left hand side, if I add 2 here, I have 3 over 4, I think, right? That's 3 over 4. And from here, I have just 11 over 12 anyway. So the difference between those two is going to be 1 over 6. So I have for x equal to 2, the probability is 1 over 6. And for 3, again, I'm going to have to check 3 as well. There are no, calculations here. I'm just going to take the, difference between 1 and 11 over 12, which is 1 over 12. So as you can see, we have 1 over 4 for x is equal to 1, 1 over 6 for x equal to 2, and 1 over 12 for x equal to 3. They are taking differences. We are taking differences to find this one. Again, for 1, we are taking the difference of this one and this one where b is equal to 1. For 2, we are taking the difference of this one and this one where b is equal to 2. And for 3, we are taking the difference of these two. There is no b in there, so it doesn't really matter which b we are talking about, but we know that it's 3. And then for part B, now find the probability that x is between 1 over 2 and 3 over 2. There's a slight mistake here, I haven't corrected it yet. But the thing is, when you're talking about this one, we can just annotate it and, it's easier that way, draw it. And there's the numbers. We have here, here, and here. Now, let's say that this is 1 over 2. This is 1. And this is 3 over 2. Now, when we are talking about between, okay, when we're talking about between 1 and 1 over 2 and 3 over 3, let's do it like this. We are talking about this part, okay? We are looking for this part. But we can also use this one. Now, if I want to find this one, I can just say that, okay, I know that there is a cumulative distribution function for 3 over 2 and 1 over 2. If I take the difference between these two values, these two arrows, I will find this part anyway. Can you see it? If you take the difference between these two arrows, okay, this is the cumulative of 3 over 2. Let's just write them here. So this is the f 3 over 2, and this is f 1 over 2. If I take the difference between these two, I'll find this part. So when I'm looking for, let's say an interval, probability of an interval, I can just find the starting and ending points, the upper and lower points of that interval in cumulative distribution functions, and then take the difference to find that probability value. So I can just use this, okay, instead of finding this one, okay, I can just pick those two f values, find the numeric values for these two and then subtract them from each other. So I'm going to take a look. I'm taking a look at 1 over 2. So for 1 over 2, I know that it's 1 over 8 from here. Okay, it's 1 over 8. For 3 over 2, here it's 5 over 8. When I pick 3 over 2, it becomes 5 over 8. So the difference is 4 over 8, which is 1 over 2. As you can see, it's 1 over 2. The mistake in this slide is these values should have been less than or equal to, not equal to, but less than or equal to. Because we are trying to find the f value exactly. Because these values are 0. These two values are actually 0. When you're looking for x is equal to 3 over 2, it's 0. It doesn't have any discontinuity there. So as there's no discontinuity, there's no jump, so there's no probability. There is only probability in those kind of questions. There's only probability when there's a jump in that point probability. We are talking about point probability. So there's no jump there. So these values are actually 0. This is a mistake. It should have been less than. Okay. So exercise 2. Airlines find that each passenger who reserves a seat fails to show up with probability 0.1 independently of the other passengers. Teeny-weeny airlines always sell 10 tickets for their 9-seat airplane, while Blockbuster Airlines always sell 20 tickets for their 18-seat airplane. Which airlines companies overbook more often? Let's say in the first one, we have 9 passengers, 9 seats for passengers and 10 passengers. If all the passengers come, it will be overbooked. So we are making a trial again. We have 10 different passengers, so the number of trials is 10. And we are looking for the scenario where all 10 of them come. So all 10 of them are successes. All 10 of them are successes. So the success rate is 0.9 because not coming is 0.1, as you can see here. So coming is 0.9. So 10 out of 10 will come, 10 choose 10, with 0.9 probability. So 0.9 over 10, 0.9 to the power of 10. And the rest, 0 people, won't come. So 0.1 to the power of 0, which is going to give us 0.35. Okay. The second one is 18 seats, 18 places to sit, and 20 passengers. Now, we will be overbooked if all 20 of them come, or if 19 of them comes. So both cases should be, calculated and then sum together. For 19 people, this is the formula. So as you can see, 20 pick 19, we are picking 19 people, 0.9 to the power of 19 and 0.1 to the power of 0. This is going to be 1, not 0.1. Again, I have a mistake here. 0.1 to the power of 1. If all of them come, it's 20 choose 20, 0.9 over 20, and 0.1 over 0, which is 0.39. So as you can see, the second airline, the Blockbuster Airline, is overbooked more often because it has a probability of 0.39, which is greater than 0.35. So it's overbooked more often. This one is a bit long question with a long answer, but the thing is, if you find the outcomes easily at start, it's just going to be easy to calculate after all. A salesman has scheduled 2 appointments to sell encyclopedias. His first appointment will lead to a sale with probability 0.3, and his second will lead independently to a sale with probability 0.6. Any sale made is equal to be either the deluxe model, which costs $1,000, or the standard model, which costs $500. Determine the probability mass function of X, the total dollar value of all sales. So our random variable is X. This is the total value of sales. So what is the lower and upper limit of these sales? The lower limit is easy. We can't sell anything, so it's 0. The upper limit, I can sell 2 different encyclopedias, the deluxe model or the standard model. And we are looking for the upper level, so we have to pick the pricier, expensive one, the more expensive one, which is the deluxe model, $1,000. And I'm going to make 2 appointments, so I can sell it 2 times, which is $2,000. So I have values between 0 and 2,000. The outcomes will be between 0 and 2,000. And the outcomes themselves will be 500, 1,000, 1,000, and 500. So total of 5 outcomes. Why? Because I can go and sell 1 normal standard model and not sell anything else. So which is going to make me net me $500 dollars. Or I can sell 2 standard ones, which is going to give me $1,000, or 1 deluxe and no sales, again $1,000, and it can be replaced. no sale and 1 deluxe, etc. And I can sell 2 deluxe, which is going to give me $2,000, or I can sell 1 deluxe and 1 normal, which is going to give me $1,500, $1,500. So I have 5 different, outcomes. So I have to calculate the probability for those 5 different outcomes. To start with, 0, no sales. Okay, my sale probability was 0.2 and 0.6. No sales means 0.7 times 0.4, which is 0.28. 1 sale and selling 500. Okay. With $500, I know that I have sold 1 regular encyclopedia, but I don't know who I sold to, so I have to check both of them. So let's start with the first one. I prefer to sell to the first one, let's say. So 0.3 times 1/2. Why? Because I'm picking the encyclopedia. The sale has happened, so I'm picking the normal encyclopedia, and the second sale hasn't gone through. 1 minus 0.6. Or the first sale has gone through, the second sale happened, and this is picking the encyclopedia. So this one is a total of 0.27 probability. The third situation where the income is $1,000. So I have 3 different, scenarios for this one. I have sold 2 standard, encyclopedias, or I have sold 1 encyclopedia that is deluxe to the first one and no sale to the second one, or I have sold nothing to the first one and a deluxe one to the second, customer. So I have to calculate all those 3 scenarios. The first one, as you can see, is selling to the first one. The second one is selling to the second one, and the third one is selling them both smaller encyclopedias. So the total is 31, 0.315, and x is equal to 1,500. So I have sold 2 encyclopedias. One of them is the deluxe one, and the other one is the standard one. I'm starting with whichever I want. I don't care. So this one might be selling the standard one and deluxe one, and this is the deluxe and the standard one, which is going to give me 0.009 probability. And in the last one, I'm selling twice. Both of them are the deluxe models. So 1/3 times 1/2, 0.3 times 1/2, 0.6 times 1/2. These are selling probabilities, and these are the deluxe ones, picking the deluxe models. And this is going to give me 0.045. Now, this is my PMF, the mass function. As you can see, all outcomes and the probabilities of those outcomes. This is the PMF. And then we are going to have to calculate the, let's see, expected value and the variance. Now, expected value can be calculated by multiplying these outcome values with their respective probabilities and then summing them up. So 0 times 0.28 plus 500 times 0.26, etc. We get a total of $675 expected value of. And the variance is going to be, now in here, we are using the formula where x minus mu is used. So x minus mu square, okay, times the probability of x. X minus mu square times x, probability of x. X minus mu, as you can see here, we have 500 minus 765 square times the probability of 500, etc. So x minus mu square times the probability of x. When we sum these up, we get $309 for our, variance. Another,
Hocam
efendim,
bir şey sorabilir miyim?
tabii ki.
Bu x eksi mu'de neden karesini alıyorduk? Onu bir daha anlatabilir misiniz?
Formül, varyansın formülü.
Yani mantığı uzun bir ispat falan mı var? Mantık
Evet.
olarak tamamlamalı mı?
Evet, uzun bir ispatı varsa ama şöyle düşünebilirsin. Şimdi senin, tamam mı, şeyden uzaklığına, you're looking for the distance from your mean, okay, expected value, and that distance should be positive. So you are just taking a look at the difference between your mean and your current value, and you're taking the square of it so that it's a positive value. There are some, mathematical, of course, notions for that one, but it's not that important for you right now. What you need to know is variance is the distance, the spread from your middle point or your expected value. And this one can be calculated in 3 different ways for you at least right now, which is, this is one of those ways. You can use the x square minus e square part. So you are just looking for the expected value of x square minus the square of expected value of x, or you can use this one, or you can use another one you can find. But still, this is just a formula, and we're just plugging in the values in there to find the value. And this one, again, another cumulative distribution function question, as you can see. And in here, the numbers are just numbers. There are no variables in there, which is going to make this much more easier. For example, it's asking us to draw the probability mass function of x. Draw, so I have to graph it. And I have to find all the probability values for all the critical numbers, all the critical parts, okay? So, for example, 0, 1, 2, 3, 4, 5, and 6. There can be jumps in any one of those points, okay? But the rest of them are the same, so there are no jumps there. So, when you take a look at 0, you can see that when x is less than 0, the cumulative distribution, the CDF is 0. But when x comes to 0 and goes to 1, up to 1, it's 0.06. So there's a difference, there's a jump at point 0, from 0 to 0.06. So the probability of 0 is 0.06. The same jump occurs at 1, but the jump distance is 0.13. So probability of 1 is 0.13. Then it occurs again at point 2. The probability of point 2 is 0.20. The difference is 0.20. Then at 3, then at 4, you can see all the jumps and all the values in there. So you can just find them. For example, at point 6, it's 0.03, at point 5, 0.05, at point 4, 0.25, and at point 3, 0.28. You can find all of them together and then graph them like this one, as you can see here. This is the PMF of x, okay? Then it's asking, find the probability that x is greater than 3 and x is between 0, 2, and 5. Now, this can be found using the PMF easily. X is greater than 3 means that you're not going to take the these values, just take these values, 4, 5, 4, 6, which is going to give me 0.33. Yes, 0.25 plus 0.05 plus 0.03. This is going to give us 0.33, as you can see here. And it's asking the probability of x being between 2 and 5, which means that 2 and 5 are not included. So I'm just going to check 3 and 4, which is 0.53. Total of 53, as you can see here as well. 0.28 plus 0.25. And then the expected value, okay, just multiply these values, multiply these probabilities with their corresponding, outcome values, and then add them together, as you can see, 2.8. And it's asking for the variance, I guess, right? Yes, variance of x. So I have to find the expected value of x squared. I'm just going to take the square of all these values and then, multiply them by their respective probabilities and then add them together. As you can see, it's done here. So it's 9.78. And I already had found the expected value of x. So I'm just going to take the square of it and take the, difference between them. It's going to give me 1.94. This is the variance that I was looking for. Another question. Now, this is an approximation one, and a very common type of question. If you buy a lottery ticket in 50 lotteries, in each of which your chance of winning a prize is 1 over 100. Okay, think of it. This is like a binomial random variable. You are making a trial, and you are making 50 different trials. Each of them have a probability of 1 over 100 to win the prize. What's the approximate probability that you will win a prize exactly once? Okay, approximate says use something other than binomial. In this case, it's Poisson, of course. Use Poisson in this case, but still, exactly once. Now, if it says exactly once, I just have to find the value of lambda and then use 1 as I. I will be 1. So, n times p is lambda, because I know that n times p is the expected value. So, n is 50, p is 1 over 100. So, n times p is 1 over 2. So, 0.5 is the lambda. Then, all I have to do is just plug that in with x is equal to 1, which is going to be I is equal to 1, as you can see here with Poisson, and lambda is equal to 0.5. Instead of, calculating this one, I will calculate this one, which is going to give me 0.30 probability. And at least twice. Now, this is a bit trickier because when it says at least twice, okay, I have to check 0 and 1 as well. Because when I say at least twice, you are just excluding 0 and 1. So I have to find the probabilities of 0 and 1, which I have found one of them in the earlier stage anyway, and then subtract that from 1. So 1 minus x is equal to 0, probability of x is equal to 0, and probability of x is equal to 1 as well. When you calculate these values, all you have to do is just plug in the parameter value and the I value which you are given here. You already know this one is 0.30. You find the value for this one as well, and this one, the total operation is going to give you 0.09 probability for, you know, at least twice, winning a prize at least twice, which is not very probable. Now, this one is a trickier, I guess. Now, there are n chips in a ball, numbered from 1 to n. You draw a chip, you take a look at it, and then you draw, throw it back and draw another chip. When you're drawing that another chip, if that chip is the same as one of the chips you have drawn so far, you end the question, then it's done. You cannot keep going. But if it's different, you put it back and draw another one, and you keep going like this, on and on and on. Now, in here, it says that let x be the number of drawings required to accomplish this objective. So picking the same chip twice, not in a row, in any way possible. Find the probability mass function of x. Now, it says that to find this PMF, you can use this identity. Now, why do we use this identity? We can see, again, here. Let's say that this is k minus 1 and this is k. Right, it's k minus 1. And k. Now, in here, when it's saying this probability of x being equal to k is equal to this one. Probability of x is greater than k minus 1, so this one. But this is not equal to, greater than only, so I know that I have this one as an open-ended one. And then I have this one as well. And like this. And this one gives us the probability of x is being greater than k. Now, the difference between those two is the area over here. And this area has k in it as well. Because k is open, so k must be in this area as well. Now, in this area, which includes k, any value other than k does not have any probability. It doesn't have any probability. They have a probability of 0. They don't occur at all. So this difference will give me the probability of k, because this is the only point where there's a probability. So this holds. This is okay. So to find this one, this is the x is equal to k is the backbone or the basic level of PMF. So I have to find it for all k anyway. So to find this PMF equation, I have to just find these two. Now, this one says that x is greater than k. This means that the first k chips are all different. They're all unique. They're not the same at all. Okay. If x is greater than k, we know that the first k chips are equal, are different. They're not equal. There's no same chip in those k chips. So I have to find the probability of drawing k different chips. Okay, this is easy. I already know that I can pick k chips out of n chips, n to the n choose k. And then I will just order those k chips, k factorials. This is the number of times I can pick those k different chips out of n chips. I already know that all of the possible combinations for this n to the power of k, because each time I have n chips in there, I'm taking one, looking at it, throwing back, and drawing another one. So if I pick chips k times, all possible scenarios, the sample space has n to the power of k elements in it. So this is my probability for picking k different chips, okay, in k times, in k trials. Then I can find this one as well. X is greater than k minus 1. Okay. This says that all k minus 1 chips are different. So instead of k in this formula, I can just write k minus 1, the same formula, just write k minus 1. Okay. Then I will just subtract them from each other. When you subtract them from each other, you can just open up the combinations and simplify all the values and factorials, etc. And then you get this one. This is the probability that you're looking for. Now, last question. A marksman, a person skilled in shooting, takes 10 shots at a target and has probability 0.2 of hitting the target. Not that skilled, I guess. With each shot, independent of all other shots. What's the probability of scoring no hits? Okay, shooting something, hitting it is a success. This is a trial question once again. So it's a success hitting it. It has a success rate of 0.2. P is 0.2. N is 10 because I'm taking 10 shots. What's the probability of scoring no hits? I is 0. Okay, then I'll just say X is equal to 0. Oops, let's just clear this one by the way. So I'll just say I'm going to find the probability of X is equal to 0. I already know that N is 10 and P is 0.2. I'll just plug those in. This K is 0. So the value that I'm going to find is 0.1074. Now, in the second part, it says that what's the probability of scoring more hits than misses? So more hits than misses is 6 hit, 7 hit, 8 hit, 9 hit, and 10 hits. More hits than misses. So I'm just going to have to pick any value from 6 to 10 for K and keep calculating this one, which is, as you can see, very small. 6 out of 1,000, I guess. And then for C, suppose the marksman has to pay $3 to enter the shooting range and he gets $2 for each hit. Let Y be his profit. Find the expectation and the variance of Y. I mean, here we are looking for the expectation and the variance of Y, all right? And this one has a formula, as we know, for the expectation. But this is actually very easy because it's binomial random variable and it was N times P. So for any 10 shots, we have a probability of getting a hit of 0.2. So my number of expected hits is 2. 10 times 0.2. So I have 2 hits expected. And I'm going to get paid $2 for each hit. So it's going to make $4, total of income of $4. And I'm going to pay $3 at the start for entrance. So I'm going to be left with only $1 at the end, as you can see. This is my expected value. And then the variance of Y. Now, the same thing applies here as well. I know that Y is equal to 2x minus 3. This is my income as well. So I have to put it into the variance formula. As you can see, it's 4 times variance x because minus 3 is gone. Variance doesn't care about the constant values, and this coefficient goes out being squared. So 4 times variance x. Now variance x for binomial random variable. Again, something we know. N times p times 1 minus p, which is going to give us 6.4. And the last part, D. Now, in D, it says that now assume that the marksman enters the shooting range for free and gets the number of dollars that is equal to the square of the number of hits. So instead of getting paid $2, if I have hit 4 items, 4 targets, then I'm going to be paid $16. This is square of that hits, number of hits. So at this point, let Z be his profit. Find the expectation of Z. Okay, if I hit 1 target, then it's 1. If I had 2 targets, it's 2 to the square, and if it's 3 targets, it's 3 to the square, etc. I don't want to find all of these values. I'm looking for the expectation of x squared right now, right? I already know the variance and the expectation of x, so I'm going to use that information. I don't want to find all those squares of hits and then multiply them with the probabilities and then sum them. I don't want to do that. I can do that, it's fine, but I don't want to do that. I'm feeling a bit tired and I want the shortcut. So the shortcut is here, as you can see. I already know that variance x is equal to expectation of x squared minus expectation of x squared. So I can just send this term, you see this term, I can send this term to the other side, and I will just say that, okay, this equation holds, which is something we know. And then I already know the variance x and the expectation of x. I have already, found them in B and C. So, sorry, just in C. So I'll just add these here, plug these in here. So this is 6.4 and etc. And then I will get 5.6. Now, as you can see, oh, sorry, I don't need this one. Sorry, I'm going to just calculate them once another. C was another expectation. I'm just going to calculate them, right? N times P times 1 minus P. This is the variance of our, hitman getting number of hits. This is the variance for that number of hits. And this is the expectation of those number of hits, which is going to be squared for this formula. So 2 to the power of 2 is 4, and this one gives us 1.6. So these are summed into 5.6. Now, as you can see, in these kind of questions, more than one way is possible of calculating those values. You can just use any one of the ways you have at your disposal, but some of them are, again, as in previous chapters, easier to calculate. Okay, this one makes it easier, but you can have just said it. Okay, I'm looking for x squared. I'm just going to find all those x squared values and then multiply them one by one with the probabilities, which is very, very, very long to do because you have to find all those probabilities one by one. It's going to take a lot of time. So try to avoid using, try to avoid wasting time like this if you can. So this one is much, much, much easier to tackle.